Okay, hello everyone. So let us start our today's tutorial for week number 10. So my name is Varnit Kapoor and we'll be starting with the session. I hope everyone is revising what has been done in past tutorials and completing the assignments and watching the lectures. So let us start our session. I hope my screen is visible. So it is week 10, right? So if you all remember, in the previous lecture, did the discretization of a lot of things we did. And towards the end, we were towards the discretization of the convection term using CDS, central differential scheme, and where we defined one number that was a Beckett number. Okay. So today we will proceed further with that topic and other topics as well. No one is trying. Which one? Okay. Okay. Anyways, other students will join. Meanwhile, let us start. Okay. Hope I'm visible now. Yeah. Cool. So in today's lecture, we will be talking about the twin differencing schemes, their order of accuracy, the comparison of CDS versus upwind differencing, UDS, and we'll do some example problem as well. Okay. So let us start with the upwind differencing scheme. That is UDS. All right, just give me a second. Okay, all right. Yeah, so if you remember, there were negative coefficients in CDS schemes, okay, where we defined one number for that to check its stability, okay, where you were seeing that if you have phi of E was phi E plus phi P divided by 2 at the east face, okay, and another as well, east, west, north. So AE was DE minus FE by 2 in CDS I'm talking, okay. So here you define that it should always be greater than 0. okay, to get the stable results. So you came across that Peclet number should be less, should be less than 2 here. Okay. All right. So in this upwind differencing scheme, first thing is that you need to understand the flow direction. Okay, first you need to understand the flow direction. Suppose I have a grid, okay, like this. I have a grid like this. So suppose this is my cell under consideration. This is E node. Okay. So this is your phase E, east phase. All right. Okay. So if your flow is from left to right like this, if your flow is from, let me write it here. If your flow is from convective flow, okay, that is FE is from left to right. That means it is greater than equal to 0. Else, if it is right to left, that is, then FE will be less than 0. So what was FE if you remember? FE was rho U at the east face into delta Y. So this is your delta Y. Okay, rho U delta Y. Okay. So phi, you need to determine the flow direction here. Determine flow direction. Okay. That is in upwind direction. So upwind means the tail portion. You choose another color. This. Okay. Okay. So we can say that phi east, phi at the east face will be phi p if it is greater than equal to 0 left to right flow. Otherwise, it will be phi of east node if Fp is less than 0. So if flow is from left to right, then you will consider that phi at the east face will be phi p. Okay, because this is your upwind direction, the tail portion. Otherwise, if the flow is from right to left, so tail portion is this, Fe is less than 0. That means so phi east will be phi capital E. Phi capital E. All right. That is what I have written. Less than 0 or less than 0. Simple. So convection term at the east face. So right now I'm assuming that flow is from left to right. Okay. So it will be how you can write convection term in that scenario. Convection term will be Fe phi p if, let me write like this, if Fe is greater than equal to 0, then convection term will be Fe phi p. Phi p. Okay. Else you can say it will be Fe phi e. Fe phi e. Okay. Fe phi. So how after discretization your equation looks like? We all know that the equation looks like AP phi p is equal to summation of A and B phi and B plus beta Okay. So this was the only part for the convection term. Rest diffusion term, how it will be? It will be similar. So if I write the diffusion terms, so there AE will be DE, that is nothing but gamma east delta Y by del X east. Okay. Similarly, you will get AW will be DW. Okay. Then you will get A naught, D naught, which will be nothing but gamma N delta X by delta Y. And similarly, you can get, okay, D south as well. Your AP term will be summation of A and B minus SP del V and B term is SC del Vp. Okay, del Vp. But if convection term is there, this was for when diffusion was there. Now what will happen if convection is there? That is the scenario we need to deal with. So if convection is there, then your AP will be AP plus FE. The old AP, that is AP plus FE. Okay, using the convection diffusion equation when you are having. All right. Now you want to solve for convection diffusion equation. Just grab it what I'm trying to say. So we have still not done the convection part, only diffusion part we have done so far. Okay, so what will be the contribution from the convection? It needs to be added in the A east, A west, A north, A south, which we have not done up till here. Okay, so what will be AP? AP will be summation from all the neighbors, of course, contribution from the source terms, that will be V. Okay. So if convection is the convection part Fe is positive, Fe is greater than 0. And if you look at the original equation, if you have seen, you will bring the convection term to the right hand side. Okay, where we have the diffusion term. All right. This is a scenario when, let me write here, Fe is greater than equal to 0. Fe is greater than equal to 0, then AP will be AP plus Fe. Else, what you can say, A east will be A east minus Fe. Okay, A east minus Fe. Any doubts in understanding this? This all has been discussed by the professor as well. Okay. I'm just giving a brief what has been done. Okay. So we have 4 such conditions for each of the phase: east, west, north, south. So if you remember the equation, gamma delta rad phi east dot A east minus rho u phi of east dot A east plus other terms is equal to 0. Okay, this is your equation. All right. Now it depends. The flow is from left to right or right to left. That takes the case for getting the value of this convection term. So phi east will be Fe phi P when the flow is from left to right, or it will be Fe phi E if the flow is from right to left. Negative value of Fe. Okay. You understand? Similarly, if you have Fw as well. Okay. This was for east phase. Similarly, if you have at the west phase, if Fw is greater than equal to 0, again, flow is from left to right. Okay. Or flow is from right to left. You have to again see. The contribution will be then you will get AP value to be AP minus FW, right? Else you will get AW is equal to AW plus FW. Okay. Again, if you see the equation for the west phase, what you will write? Gamma grad phi W dot AW minus rho U phi W dot AW plus other phases as well, other contributions. Okay. So you can say that this term again will be FW phi P if FW is, this was your P node, this was your east node. Okay. Flow is from left to right. This was your, sorry, west node. Okay. Flow is from left to right. So you have to see the which direction up, and that is the tail part. So if left to right, that means FE is, if FE is greater than 0, then you will consider phi W. That is, but if FE is less than 0, then it will be FW phi. If it is right to left, then tail will be this phi. Okay. All right. Same thing I have written here. It will be FE greater than equal to 0 and FE less than 0. Here also FW greater than equal to 0 and FW less than 0. FW less than 0. Okay, again, 4 such conditions for all the phases, east, west. Okay. So what can we do? We can create a general algorithm for upwind differencing scheme. General for upwind differencing scheme. So we define a max function here. Define max function which says between two values A and B, maximum of A and B will be A if A is greater than B or B else. Okay, A is greater than B, you can say that maximum value will be A, less than B, then it means other value will be B. So you have the equation AP phi P is equal to summation of A and B, phi and B plus B. So your values will come out to be A east will be DE diffusion term plus maximum of, so contribution is playing a role in convection terms only. So right, minus FP comma 0, AW will be TW plus maximum of FW comma 0, A north will be D north plus maximum of minus FN comma 0. Okay. And AS will be DS plus maximum of FS comma 0. So diffusion terms are all positive. Okay. And your AP will be summation of A and B minus SP del V plus FP minus FW plus FN minus FN. Okay. And B term will be SC del VP. Right? If you discretize and put all the rearrange those terms, this will be your equation. So if F is greater than 0, suppose for the east phase, F is greater than 0. Okay. That means maximum of these two value will be 0 only. Okay. These two will be 0 only. If F is less than 0, so how you will write if F is greater than 0? 0 will be the value maximum of them, DE plus 0 is DE. Okay. When F is less than 0, That means this will be a positive value. Fe itself has a negative value and negative sign. It will be a maximum value. So it will be dE plus Fe. So if you will put here dE plus Fe, dE minus Fe and this contribution from Fe will cancel out. Okay. If Fe is less than 0, you will take this value minus of Fe. Maximum will be minus of Fe. So it will be, and you will do the sum of A and B's. Okay. That is AWAN, ASAP, AWAN, AS, AE. Okay. So this DE minus Fe plus Fe, this term will cancel out. Okay. Are you getting my point? So if Fe is positive, then the contribution goes to AP of that Fe. So maximum of Fe and 0 will return a 0 because Fe is positive. So minus of positive is a negative value and 0 is a positive value itself. So 0 will be taken. If Fe is negative, okay, what will happen? The contribution will cancel. Okay. Any doubts? Fe will be returned if Fe is negative. So if Fe, if minus Fe comes into play, AE becomes DE minus Fe. Okay. And then if it add to the AP, Fe and Fe cancels out. All right. And we are just left with only the diffusion part. The same is with the west case, north case, south case. Okay. All right. Any doubts, understanding? If you have any doubts, please ask. And this is how you can write the AP terms, B terms, and all the individual neighboring terms. So if you observe, what have I written? Finally, question is summation of A and B minus SP del V. Hello, am I audible? Hello, am I audible? Hello. Okay. So what about the coefficients now? The question arises, what about the coefficient? So all the A and B's are positive. Okay. All the A and B's are positive. If source is 0, then you can say that if source is 0, if this term is 0, this is the only negative term if it is creating an effect. All right. So AP will be summation of A and B. AP will be summation of A and B. So what happens to your Scarborough and boundedness is the question. I think just what I'm trying to say. So we had made a compact form of a general algorithm for UDS. A general algorithm for UDS. So my question is, what about the coefficient? So if you look at the coefficient, what is the property? All the coefficients are positive. If Fe is like the diffusion coefficients are always positive, these are always positive, right? Diffusion coefficients, dE, dW. What about the convection part? If this is negative, this will become positive. So we have seen that if the effect of this is coming, then this will cancel out. Okay. If the effect of this is not coming, this self is 0 and this self is positive. Okay. So that means all the A and B's for each of the phase will be positive. But if there is no source, an incompressible flow is there, which satisfies the continuity equation. That is the mass conservation equation. So what will happen to the term? The entire term will become 0. Okay. If it is satisfying a mass conservation equation, that means we have Fp minus this entire term. This entire term, Fe minus entire term would be equal to this whole term, sorry. This whole term will be 0 because it is satisfying the mass conservation. If source is 0, incompressible flow equation is there. That means all the convection terms and this will become 0 and you will be left with only AP is equal to A and B, summation of A and B's. Okay, summation of A and B. So that means all A and B's are always positive. So that means it satisfies the Scarborough criteria inequality in the equality. Okay, not inequality. So Scarborough criteria is satisfied for equality as well as boundedness is also guaranteed. So I'm writing here if source sum is 0 and del dot u is equal to 0. Okay. So this implies Scarborough satisfied for equality as well as boundedness guaranteed. Okay, because your AP will be now summation of only A and B. This much. Okay. Because AP 5P is nothing but summation of right here. AP 5P is nothing but summation of A and B, phi and B. All right. The boundedness is also guaranteed. So we have developed a new scheme which satisfies the Scarborough criteria as well as boundedness, which is much better than we had before. Okay, where coefficients are coming out to be negative in UDS. Okay, so what can you say here? So unlike central differencing scheme where mesh is kind of restricted to Peclet number condition, but it turned out that the upwind differences scheme is quite diffusive. All right. Bounded test satisfied, Scarborough satisfied. The mesh can be taken off anything. It is not dependent over the Peclet number itself. Okay. So we can work with diffusion with finite grids. Okay, which can smear out the discontinuities if it is happening. If you say that gamma is 0, diffusion term itself is 0, where UDS can smear some discontinuities. Okay, in the solution of phi. So because of this, UDS can be used as an initial solution, but it is quite diffuser. Diffuser terms are coming out there. Okay, in the last tutorial, if you see. So as a result, we will look some of higher order upwind differential scheme, which are better in terms of not having such high diffusion such as the UDS. Okay. If you see here in the upwind differencing scheme, first of all, tell me this much is clear. We understood that Scarborough and boundedness is completed. It is satisfying if source is 0 and incompressible flow is following. But if you consider a situation where discontinuity in the problem is there and there is no diffusion, let us say gamma is equal to 0 in our equation. The diffusion terms gamma is equal to 0. And there is a discontinuity in the solution of phi, then it can actually smear some discontinuities. It turns out to be diffusive, and this will explode the behavior. Okay, this will explode the behavior of the problem. So because of this, the upwind differencing scheme can be used as an initial solution, but it is having diffusiveness in the nature. So we will look for higher order upwind differencing scheme, which are better in terms of not having such high diffusions as in the UDS. So we'll look in the later part of the course. So as of now, we have learned two schemes, central differencing, upwind. So both of them we have looked in terms of their properties, how to implement them in a particular code, okay, to create an algorithm. Now we'll come across with the order of accuracy of CDS and UDS. Of CDS and UDS. Suppose if you have a uniform mesh once again, this is your P node, this is your this node, this is your east node. Okay, spacing is del x, del x, alright, del x and del x. This is your east, this is your west space, and again this is also del x. Okay. It's a uniform mesh 1D. So if you want to expand phi at property phi at P, expand phi P about phi east. Okay. We have a uniform mesh with a spacing of delta x for each and every cell. We use our Taylor series expansion here again to expand phi about phi e. Okay. So phi e about phi e. I'm saying phi p about phi e. Okay. All right. So how you will write? Phi p will be phi e. So about phi e, it is at minus del x by 2. Minus del x by 2, dou phi by dou x about e space plus, because minus x square will be positive only, dou phi by dou x, dou 2 phi by dou x square, and order of del x cube. Okay. Now, if you want to expand phi e about phi e, so for about phi e is at plus del x by 2. Okay. So how you will write phi p, sorry, phi e will be phi e plus del x by 2 dou phi by dou x about e space plus del x by 2 whole square. I missed one term, mistyped here. 1 by 2 factorial del x by 2 whole square by 2 factorial dou 2 phi by dou x square plus order of del x cube. Okay. So from the first equation, if you rearrange this and this to here, or what you can do, phi e you can write. So this term will come out to be here. So how you will write from the first equation? This is your first equation. This is your second equation. So from equation 1, you can say that phi east will be phi p plus order of del x plus order of del x. Okay. You are taking the truncation like this. Okay. Similarly, if you observe for UDS, if your Fe is greater than 0, so phi e will be upwind differencing scheme. For upwind differencing scheme, you know that if Fe is greater than 0, left to right, the tail is here, so phi e will be phi p. Just now we have seen. For upwind differencing scheme, phi e will be phi e plus, sorry, for upwind differencing scheme, if F is greater than equal to 0, then phi E will be phi P. So only first order accurate. This is same. We have taken the truncation error as first order accurate. So that means it is first order accurate. All right. And now if you add one, take average of equation 1 plus 2 by 2, then you will get phi at east, which will be phi E plus phi P by 2 minus del x whole square by 8, you can say, rho 2 phi by 2x square about east and so on, right? Rho 2 d2 phi by dx square about east, right? If you just apply the operation, that is 1 plus 2 by 2, equation 1 plus 2 by 2. So if you see the CDS, in CDS, they use a central difference scheme. Your phi east was phi E plus phi P by 2 plus order of del x square, order of del x square. Phi E plus phi EP by 2, similar, and order of del x square. So you can say it is a second order accurate. It is second order accurate. Right? Any doubts? We have got the accuracy of the order. Let us do one example problem. If you have any doubts, Celia, please ask. Sushant, any doubts? Just take a minute and understand. If you have any doubts, so we are going to deal with 2D pure convection equation. Try to solve it. Take a minute. How you will think for a pure convection equation. Okay, then let us start solving pure convection problem. Suppose we have a domain. Okay, where you have phi is equal to 0, boundary values. Phi is equal to 1. This is y. This is x direction. Okay, this length is L. All right, and you have a velocity that is known velocity 1 I cap plus 1 j cap. Okay, 1 j hat. Gamma is equal to 0. No diffusion is there. Peclet number is defined as rho u delta x by gamma. So that means Peclet number will turn out to be infinite. What should be delta x? As per CDF, for Peclet number to be less than 2. Only pure convection equation. That means your equation is del dot rho u phi, del dot rho u phi is equal to 0. This is your equation. Simple. Now think how you will try to do. Nishant, you have done? If you have done, please tell me. It's a pure, okay, let me do. If you guys are not getting, there's a pure convection equation. No diffusion is there. Gamma is equal to 0. No source term is there. Pure convection, del dot rho u phi equal to 0. Okay. And we have given the velocity field I cap plus j cap. That is at 45 degrees from the axis. Like this. Right? So theta is the 45. This is the flow field. It kind of goes away and leaves in the domain. So we are considering a square domain L by L dimension. So this is also L. So this is also L dimension. No diffusion is there, but we are interested how the scalar get transported. So we have the scalar given value phi that is equal to 0 on the left boundary, vertical boundary, and okay, so it is a phi value equal to 0, and the horizontal value phi is given to be 1. Okay. If you observe that if you release some dye is going to convect, and it is not going to because of the diffusion. It is not going to diffuse because there is no diffusion. That means everything because of the flow is angle at 45 degree, everything that originate from here would go, and this would entire thing would filled up with phi equal to 1, or everything is getting convected. So in this entire thing would be phi equal to 1, and whatever is on the top would be equal to phi equal to 0. So essentially this entire thing would be filled with phi equal to 0, and right, this entire thing would be filled equal to phi equal to 0. But there is no diffusion. So there you will see an abrupt jump along the diagonal, because if you observe this section, above section is having phi is equal to the left hand side of the portion. Till here is having phi is equal to 0 region, whereas this is phi is equal to 1 region. So at this 45 degree, there is going to be a jump from phi is equal to 0 to phi equal to 1. Okay. Because change from 1 to 0. Okay. Thickness, what what is the dependent thing here is the thickness of the layer. This layer at 45 depends the amount of diffusion you have. If you have a larger diffusion, this layer would have a thicker and thicker. Okay. Or in a limit of gamma equal to 0. So this layer kind of thing would exist in which the phi value changes from 1 to 0 at a diagonal value. For the present problem, we do not have gamma. We have to assume that gamma is equal to 0. So there is no such layer. This is the exact solution. Now, if you have to calculate the cell Peclet number, which is rho u delta x by gamma, this would be infinite. Okay. So if you solve this kind of problem, what kind of graph you are going to expect here is that I'll just plot the graph. Solving you have to do for the problem. This is phi versus y. Okay. In the y direction, what is happening? The value is changing from 1 to 0. How? The actual solution should be like this. Okay. This is the exact solution. Exact. When you are dealing with a UDS, upwind differential scheme, you will observe some diffusion term which is at the okay, which is creating a diffusion in the problem. This, whereas CDS will create some oscillations because of Peclet number conditions. And again, something like here, some oscillations will be there. So this will be your UDS, and this will be your CDS. Okay. So the numerical diffusion happening. We have already discretized this thing and discussed about. I guess this part you can do. So we have understood upwind differencing scheme, order of accuracy of CDS and UDS, and this example problem. Now we are going to start with numerical diffusion and dispersion and unsteady convection. So CDS produces oscillation at its dispersion. whereas UDS produces smeared out solution, that is because of the diffusion which was happening. Okay. So what we are going to look again in the solution is that numerical diffusion and dispersion is happening, artificial diffusion and dispersion that are obtained in UDS and CDS respectively. So we are going to see this in the form of numerical perspective. What is the kind of behavior? How we can explain this behavior from the equations? So we are going to analyze this thing today. I've just made it so far. Now let us analyze. You can do as well. Let us analyze. So that is why we are going to analyze today. And depending on the time, we can also and say, look how the unsteady equation will be doing. Let us see what happens, okay, between these two schemes. So when CDS is happening, we say that produce oscillations. Okay, that is dispersive. Whereas when UDS is happening, it produces smeared out solution. That is nothing but diffusion. All right. So this can be helpful explained using a model equation. So your convection problem was L dot rho U phi equal to 0. Okay. In 2D, how you will write rho by dou x of rho U phi plus dou by dou y of rho V phi equal to 0. Okay. Rho by dou x of dou U phi and dou by dou y. And you assume that rho is equal to constant. Assume and U is given to be ui hat plus vj hat, and both u and v are greater than 0 and are constant values. Okay. So now you will apply the FVM scheme for discretization. So about the control volume, del dot rho u phi dv is equal to 0. So apply the GDT, you will get rho u phi at phase dot a at phase equal to 0. Right? Your equation, because this is the convective part, so rho u is nothing but f. So Fp phi e minus Fw phi w plus F north phi north minus F south phi south equal to 0. Okay, where east and west F's are equal, that is rho u delta y, and north and south Fe will be rho v delta x, because in y direction v is there. Okay. If you use upwind differencing scheme, how you will calculate the phi? So using UDS, if you use UDS, so phi east will be phi p. Okay. Phi west will be phi w. Phi north will be phi p. Phi south will be phi south. Okay. We have seen how the tail part of that is taken. Put all these values now, all these values in this equation. Okay. So let us put. Your equation will come out to be rho u del y phi p minus rho u del y phi w plus rho v del x phi p minus rho v del x phi south equal to 0. Now you divide by del x del y. Divide by del x del y in whole equation. You will get your final equation as rho u phi p minus phi w by del x plus rho v, and rearrange it, phi p minus phi s by del y equal to 0. Okay. So these are your two equations. So first equation, let us assume that this is your first equation. No, not this one. This is your first equation. And after resolving, rearranging, your second equation is this. Okay. Now you need to expand. You need to have phi W and phi south about phi P. Let's expand because these are the, we don't know these values. So expand phi W and phi S about phi P using Taylor series. Okay. Yes. So phi W will be about the west, phi P is towards the left, phi P. So if you have a 2D kind of thing, so this is P, this is W, this is north, this is east, this is south. So you're getting phi at west phase about phi at P. So it is at plus del x by 2, right? Or minus del x by 2. Expanding phi W and phi S about phi P. Oh, sorry, about phi P. Sorry. Good. So about phi P, this west face is at minus del x by 2. Okay. So that will be minus del x by 2 dou phi by dou x about P plus, I'm removing this, del x by 2 whole square by 2 factorial dou 2 phi by dou x square and some higher order terms. Okay. Right. Similarly, phi south, phi P is minus del y. So why I'm taking del x by 2. Okay, sorry. These are the capital values. So these will be not del x by 2, del x square. I mean, if you see about P west value is calculating, that is at minus del x. About P, this is at minus del x. Okay. Similarly, minus del y. Dou phi by dou y at P plus phi by dou y square and so on. So in order to substitute in equation 2, we will arrange these. Okay, you need to have phi W and phi south. Now you will put the values. So phi P minus phi W phi del x you will do. So what you will get? The equation phi P minus phi W by del x, because that is what we only want from here. Okay, phi P minus phi W. Next, that is dou phi by dou x about P minus del x by 2 dou 2 phi by del x square about P and so on. And phi P minus phi S by del y will be dou phi by dou y about P minus del y by 2 factorial dou 2 phi by del y square about P and so on. Now substitute these two values in equation 2. Substitute in 2. After substituting, okay, and rearranging, your final equation will come out to be, I'm just writing the final equation, rho u dou phi by dou x plus rho v dou phi by dou y is equal to rho u del x by 2 rho 2 phi by dou x square plus rho v del y by 2 rho 2 phi by dou y square plus order of del x square plus order of del y square. Okay. So you can assume that u and v are also equal, delta x, delta y will also be equal. Okay. So we'll get a model or a modified equivalent equation. So what will be the final equation? If u and v are equal and del x and del y are equal, your final equation will come out to be in a vector notation. I'm writing rho u phi is equal to del dot rho u del x by 2 grad of phi. So if you see, this is a kind of a diffusion term has come now. Using upwind differencing scheme, you see that there is a gamma effective happening here. But we wanted to solve a problem which was only del dot rho u phi equal to 0. So some right hand side, some extra term is there. That is nothing but a diffusion term, just creating a smear kind of solution. So this is an artificial diffusion coefficient. If we needed, we get this is nothing kind of artificial diffusion. Okay, we got some kind of artificial diffusion here. All right. So which is proportional to delta x. So if you want to reduce this artificial diffusion, you need to have a very spinor grid. Delta x should be very small. Okay, so that gamma effective will come out to be 0. Okay? Your extra diffusion test. Now, if you solve this using pure convection equation using CDS, okay, using CDS solve del dot rho u phi equal to 0. Again, rho constant, u v greater than 0 and constant values, that condition we will take. Okay. So you will again get an equation like this. You have an equation like this, Fe phi e minus Fw phi w plus Fn phi n minus Fs phi s. This was your equation. Okay. Now question arises, how you will get the phi east, phi west, phi north and all those terms. Okay. So let me rearrange and write rho u del y phi east minus phi w plus rho v del x phi north minus phi s equal to 0, because you know f is nothing but rho u del y. Okay. Now in CDS, your phi terms will be phi east is phi e mean of 2. That we have done. Phi west, phi p plus phi w by 2, phi north plus phi p by 2, phi south, phi p plus phi s by 2. Okay. Now you put the values and divide through delta x, delta y or the way. Put the values in this. Yes, we will get and divide by delta x, delta y. So phi e minus phi w by 2 delta x plus rho v phi north minus phi south by 2 delta y. This is capital W. Okay. Now again, you need to expand about Taylor using Taylor series phi east and phi w about phi p. Okay. Now expand phi e and phi w about phi p using Taylor series. So again, you will have phi east is nothing but phi p plus del x dou phi by dou x p plus del x square by 2 factorial dou 2 phi by 2x square plus and so on. Similarly, phi west will be phi p minus del x dou phi by dou x about p plus del x whole square, rho 2 pi by 2x square, and so on. Okay, all the remaining terms. Okay. Now you will take out phi e minus phi w by phi e minus phi w. Okay, phi e minus phi w. You will take a difference of it and divide by 2 delta x. So what you will get? So this term will cancel out. Then you will be having phi e minus phi w, both will add up. This will give you 2. So your phi e minus phi w will give you what? Dou phi by dou x, del x square by 6, dou q phi by dou x cube about p, and so on. Similarly, you will expand north and south about p. You will get phi north minus phi south 2 del x, dou phi by dou y, del y square by 6, dou q phi by dou y cube about p, and so other terms. Okay, and substitute back in the equation and rearrange. Substitute back in this equation A. Suppose this is equation A. Substitute in A and rearrange. What will you get? Final equation. Your final equation would be something like dou by dou x of rho u phi plus dou by dou y of rho v phi, because it's two-dimensional, and some extra term will come, rho u del x square by 6 dou q phi by dou x cube plus dou q phi by dou y cube, and some other terms. Okay, so truncation error is of del x square. Okay, so CDS is second order, but you wanted to solve only this part, and here you wanted equal to 0 for pure convection. Okay, so there, if you observe, you wanted to solve, but there are some oscillation behavior here. This is a dispersive term. Okay, this is a dispersive term. In UDS, you are having some diffusion term. In CDS, you are, because it's not. I must say that in the order of leading truncation is delta x square, so it is second order accurate. Okay. It is not directly a diffusion. Diffusion is rho u delta y by del x, or delta x by del x, something like that. Rho u delta x by gamma. Okay, so, but here it is of order of 2, delta x square. So CDS is second order accurate. Okay, second order accurate, but with some dispersive terms. All right. Now, if you come across with unsteady convection equation, then there will be. So I've explained the behavior why there was a graph, oscillations and dispersiveness. Now let's come to unsteady convection. If you have unsteady convection equation, that means dou by dou t of rho phi plus del dot rho u phi is equal to 0. Okay. So if you consider a 1D scenario, then it will be, this is a vector form for 1D, rho by dou t of phi. If you assume also the rho is equal to 1, let, then it will be dou phi by dou t plus del dot, oh sorry, not del dot, dou by dou x of u phi equal to 0. This is our equation, and this is a linear wave equation. This is called as a linear wave equation. So only linear reduction is happening. U is known and it's not a function of phi. Suppose you are given an initial condition and boundary condition. The initial condition is phi at x is equal to 0 will be phi naught of x. Okay. Boundary conditions at both ends. Boundary conditions. That means phi at x is equal to 0 at time t is given phi of x naught, and phi at x is equal to L at time t will be phi of xl. Okay. If domain is of length L. If domain is of length. So your exact solution will come out to be for this equation. If you solve it, your exact solution will come out to be phi of xt will be phi naught x minus ut. Okay. So suppose if your input is like some sine wave, so just displaced by ut. Okay. Was a draw a graph. Okay. This is phi versus x. Okay. So if your input wave is like it's a wave equation, but if my input is like a sine wave, equation should come something like suppose this is 0. Okay. And this is 1. This is minus 1. So your equation should sine wave input should give you a result like, okay, but after t seconds, okay, this is at t is equal to 0. After t seconds, it will be displaced by ut. This much it has displayed. Now your equation will start. Okay, this is your equation. This much is ut. Okay. Similarly, if it's a pulse wave, it will also shift accordingly for a linear wave equation. So you can evaluate the discretization schemes using UDS and CDS, whether they can predict the shift or without introducing diffusion, where smearing is happening for diffusion or dispersion, like wiggles are happening or not. Okay. So far, we have seen the numerical diffusion and dispersion and unsteady convection equation. Now we will discretize this unsteady equation. Okay. Using CDS, UDS, and Lax-Ventroff. And we'll see the higher order schemes as well. Okay. Just give me a minute. Okay, now let us solve this equation. So we will apply again. Equation we have this in 1D. So we will apply FVM technique. Because it's unsteady, we have already dealt with unsteady problems as well earlier. Okay. But earlier there we have discussed only unsteady diffusion equation. This is unsteady convection equation. Okay. This is unsteady equation. So here again, it can be written as phi p minus at phi p naught delta x plus some factor will come in the second term. That is u phi at east minus u phi at west with the factor f plus u phi at east naught minus u phi at west naught with a factor of 1 minus f, and this whole will be multiplied with delta t equal to 0. Delta t equal to 0. Okay. So if we are dealing with the first case, when it is explicit and seriously, okay, explicit means at there f will be 0. Okay. First case, explicit plus upwind differencing you are taking. So that means f is equal to 0 for explicit, u is constant. So that means phi at east will be, it is serious, not UD, sorry, serious. So phi at east is written as phi e plus phi p by 2, and phi at west will be written at phi west plus phi p by 2, right? So if you put the values there, so you will get the equation as phi p minus phi p naught by delta t plus q by 2 delta x phi e naught minus phi w naught equal to 0. This is your, and there is, and after putting and dividing by delta x delta t I'm writing. It's an explicit equation. You no need to solve for a system. No need to solve for a system. It's all right. You've seen this kind of things earlier. And this has a, in error, the truncation will come out to be of order of delta t in time and delta x square second order in space. Okay. So I'll write just points. Order of delta t and order of delta x square. For one-level stability analysis, that will give unconditional unstable result. Unconditional, really unstable for von Neumann case, von Neumann analysis, stability analysis. All right. So that means your modified equation is coming out to be dou phi by dou t plus u dou phi by dou x. You need to solve this, but no, you're not getting this. You will get again some u square delta t by 2 dou 2 phi by, like you got for pure convection equation. Some diffusion term was there. Again, here some negative artificial viscosity will come, and there will be a diffusion-like behavior. Okay. So this term will show diffusion-like behavior, and this term will show. So it cannot be used because it's a unconditionally unstable. Explicit CDS you are not going to use anyway, and it will represent negative artificial viscosity. In detail, everything has been discussed. I'm just giving the briefs. so that you can solve your assignments. Okay. So now we will proceed to the second case where you will use implicit instead of explicit, implicit CDS. Okay. Now you will implicit CDS. So implicit means F will be 1. The factor F will be 1 here. That means F is 1. So after putting the values and rearranging, your equation will come out to be 5p minus 5p naught by delta t plus u by 2 delta x by e minus phi w equal to 0. So it is a linear system? Yes, it is. At every delta t, a linear system need to be solved here. We have done all this kind of thing in unsteady diffusion equations. Again, truncation error will be there of order of delta t and order of delta x square. Okay, it will be unconditionally stable because it is an implicit scheme. So we know that from von Neumann stability analysis, unconditionally it is unconditionally stable. So your modified equation comes out to be so the modified equation for that. Here modified equation will be again you need to solve dou phi by dou t u dou phi by dou x equal to 0, but you will get del t by 2 dou 2 phi by dou x square. Okay, earlier got minus you square del t by 2 dou 2 phi by dou x square, but this time it's a positive value. Okay, it's a positive value. So it's a positive artificial diffusion. Positive artificial diffusion. Positive artificial. Stability here, stability does not guarantee that correctness of the solution. Okay, make sure that stability is it's a unconditional stability, but it doesn't mean the solution is correct. So you will rewrite your equation. Okay. So implicit CDS was equation was this. So this is your equation 1 we have. Okay. Let's rewrite this equation. The first equation will be phi p is equal to phi p naught minus u del t by 2 del x by e minus phi w. Okay. So oscillations are there because negative coefficients are there if you observe here. So if you see that oscillation will be there either you use implicit or explicit CDS. So they are of no use so far. Okay. Now if you come to the third case, that is explicit UDS, upwind differencing with explicit. Okay. So your equation will be phi p minus phi p naught by delta t plus u by delta x phi p naught minus phi w naught equal to 0. Here truncation will be order of delta t and order of delta x. Both are first order accurate. Conditionally stable. Okay. Here, conditionally stable scheme. If you do that, one Newman stability, you will get that the CFL number u delta t by delta x should follow between 0 and 1. Okay. So here your modified equation, some things look like. Write it here. I'm not solving now, just I'm writing the equation directly. It will look like dou phi by dou t plus u dou phi by dou x is equal to u del x by 2 into 1 minus nu dou 2 phi by dou x square. So nu is nothing but your foreign number, CFL number. Okay. Beautiful number. So again, this equation can be rewritten as phi p is equal to phi p naught 1 minus nu plus nu phi w naught. Okay. This above equation. All right. I hope it's clear. So for nu from 0 to 1, all coefficients will be positive. So it can be used to solve explicit under this condition. Okay. So like if you have sine wave, square pulse wave, periodic boundary conditions in the x directions. Okay. You can solve this kind of scenario. Okay. But again, you will see some kind of like if you see a convection of an initial profile, if you see it's a sine wave. So somewhat like if I draw for a sine wave, let me draw phi versus x. So if I go with exact value, this was your exact solution. But yes, using is a explicit UDS, and this is exact. Okay, of that equation. Similarly, you can see for the pulse wave as well. So some kind of wiggles are happening. Okay. Now, what will be for implicit UDS if I take? So you can do that scenario. Okay. So again, there will be order of delta T, delta X, stability analysis. You can check modified equations. You can check. Now there was one scheme. There was Lax-Ventov scheme. Lax-Ventov said that Lax-Ventov. So he wanted to use CDS anyhow. We were saying that CDS we cannot use. So there was a negative artificial viscosity was there. Okay. So he said that you start with giving this viscosity only. Okay. So instead of, let me write here, your equation was for explicit plus CDS. I'm saying the first equation. You had an equation that was dou phi by dou t plus u dou phi by dou x. You wanted it to be equal to 0, but there was u square delta t by 2 into dou phi by dou x square. You had this. Instead of this, you solve for, instead of equal to 0, you solve for plus value. That means dou phi by dou t plus u dou phi by dou x is equal to u square del t by 2 dou phi by dou x square. Solve this instead of, start with this only, instead of dou phi by dou t plus u dou phi by dou x equal to 0. You can start with this equation. Okay. So when you will start with this equation and discretize, this positive term will get cancelled out with this negative term which was coming. Okay, this will get cancelled out. So if we discretize this equation, what will you get? Phi p minus phi p naught by delta t plus u phi e naught minus phi w naught by 2 del x is equal to u square delta t by 2. This term can be, it seems like it is central using finite difference, but believe me that it is all using FVM only, not FTM. Okay. So here your truncation is order of delta x square as well as order of del t square. Okay. Second order in both time as well as space. And here the Peclet number will vary from for von Neumann stability analysis. From von Neumann stability analysis, your Peclet number will vary from u del -1 to 1. Okay. This conditionally stable. So which was unconditional stable, now it has come to be conditional stable. Okay. And you will get some modified equation again with some another terms. But yes, it is a conditional stable and this can be used now. So your modified equation will become dou phi by dou t u dou phi by dou x equal to minus u del x square by 6 1 minus u del t by del x whole square dou q phi so on. Okay. Right. So now this can be scheme used for if I plot where earlier it was not even used, getting to used. So this was your exact. This is exact. So some wiggle will happen here. It's just an overlapping kind of thing, and some wiggle will happen here, but it can be used now. Okay, in some conditions. Now you can go ahead with the higher order schemes as well. Okay. So instead of you can go with second order upwind scheme, third order upwind schemes, and so on. And there you will arise with some beam warning kind of scenario. And then you can do with third order upwind schemes. That has all been discussed in the lecture. So I have to just give the brief that how things are happening here. So higher order schemes you can go ahead with. How you can implement those higher order schemes. How you'll discretize the convection diffusion equation for unstructured meshes. How you will do that. Just give me a minute. Okay. Now let's come across for convection diffusion on unstructured non-orthogonal meshes. Convection diffusion on unstructured non-orthogonal. So all those higher order schemes have been discussed by the professor in the in their lecture videos. Okay, you can go check out all the derivations have been done. If I come across with some non-orthogonal kind of scenario. Okay, so this is your AF. Your cells and birds are connected like this. They are not aligned. So this is C naught. This is C1. They're connected like this. So this is eta direction. And so its unit vector is eta hat. And this is zeta direction. So A zeta. All right. Okay, your flow is getting connected like this, suppose. Okay. This is your phase F. Phase F. So this distance is how much? Zeta direction, so that means it's zeta. Okay. In your x and y coordinates, you can say that this is y I hat x, so y j hat x I hat. All right. So if you apply FVM, your equation is this: unsteady convection diffusion. Oh, sorry, steady convection diffusion. So rho phi by rho t, the rho phi term will be 0 plus del dot rho u phi is equal to del dot gamma grad phi plus s phi. So apply FVM, you know the equation. So far you have done for discretization and unstructured for diffusion, but not for convection part. Okay, so apply the FVM. What will you get here? So it will be summation of phases. The diffusion term will look like this: dot AF minus F. The connection term will look like this: F dot AF plus source term. All right, equal to 0. Now you know that in conventional coordinates, F is rho u delta y, FW is rho u delta y. But here, F at phase will be the rho u at phase dot AF dot AF. This will be okay. So how you can write first the diffusion term? The diffusion term is gamma grad phi F dot AF, which is nothing but gamma F by this realization we have already done in earlier lectures. Secondary gradient, primary gradients, all those things come. Okay. E zeta phi 1 minus phi naught as secondary gradient terms come along with this. So that this is nothing but if you assume that this term is EF, so you can write it as EF phi 1 minus phi naught plus secondary gradient at that phase. Okay. Now how you will write the convection term? So you will assume this was your convection term is like this. Let me write it: diffusion. Now convection is rho u phi at phase dot a of f can be written as f of f phi of, okay, f of f phi of f. Like this you can write for now. So our discretized equation again, put all the values back in the equation. So the equation will look like summation at all the faces ds phi 1 minus phi naught plus secondary gradient at faces minus f at f plus sp plus sp phi p naught plus del v naught is equal to 0. Now you will use if you want CDS. So phi e east west, phi e plus phi p by 2, phi f will, so say, similarly here, if you used CDS, so here phi at f will be, there was a east face, here it is f face. So phi naught plus phi 1 by mean of two centroid values. Okay. Simple averaging we are doing. We can do improved averaging as well. But now, for now, it's like this. So our final equation will become like AP phi P is equal to summation of A and B phi and B plus B, where A and B is nothing but DF minus FF by 2, and AP is nothing but summation of A and B minus SP del V naught plus summation at faces for FF. Okay. F east, west, north, south was there, but here it is the faces. So similar to Cartesian mesh, if we say that f at east is greater than 0, that means flow is from left to right. Here, if f of f is greater than 0, so if I say if f of f is greater than equal to 0, then what will happen? Then you can say that a and b will be less than 0 or f greater than 2 times of b of f. That is nothing but a Peclet number. If my Peclet number is greater than 2, your coefficients, neighboring coefficients will be negative. Okay. And so similar is structured in structured meshes also was happening. So for A and B to be greater than 0, this implies FF by D of F should be less than 2. This implies Peclet number is less than 2 if you are using CDS. But if you are using UDS instead of CDS here, if you are using UDS, upwind differencing, so what will happen now? So there you used to say phi at each face will be phi p if f is greater than 0. So similarly, you will say phi of f will be phi naught previous value if f of f is greater than 0, else it will be phi 1 for f is less than 0. Okay, and put the discretized equation and make us assemble the equations to get an algorithm. Okay, so discrete equation will be ap phi p is equal to summation of a and b phi and b plus b. Again, use a max function. So here df diffusion term plus maximum of minus f of f comma 0. Okay, your AP will be summation of NB A and B minus SP del V naught plus summation of FF, all the neighboring values. And your B will be SP del V naught plus summation of NB at secondary gradient faces. Okay, secondary gradient values. If you use again higher order schemes for unstructured meshes, like we did for the structured one, the you can say up in third order, up in second order schemes. Okay, what will happen? So again, you have to use a Taylor series expansion for unstructured meshes. Okay? So you can get similar kind of scenario for higher order schemes as well there. So like so you can deal with higher order scheme for structured meshes and unstructured meshes, and all that has been done by the prof in their lecture content. So I guess this is it. If you have any doubts, please ask. I'm waiting here for next 2-3 minutes. If no doubts, then it's all right. We can leave. So Nishan, do you have any doubts? I think you get dropped off in between. Understood? The lecture part, tutorial. If you have any doubts, please ask. So what all we discussed, let me again please share. So we started with upwind differencing scheme because we have done CDS in the previous tutorial. Okay, we came across with the equations and general algorithm for UDS we prepared using a max function. We checked for the order of accuracy for CDS as well as UDS. Okay, so after that we did an example problem for pure convection problem where we first saw the graphs and we saw that why there are wiggles or why there is extra diffusion time happening in UDS or CDS. Wiggles are happening. So CDS produces oscillation, whereas UDS produces diffusiveness. Oscillation and means dispersiveness. Okay. So we saw that with the help of the numerical equations, which we framed out. So using CDS, you saw the extra diffusiveness is happening. Using UDS, uh, you are seeing the extra equation, and using CDS, there was wiggles were happening, dispersiveness was happening, so negative viscosity was coming. So then we came across with the unsteady convection equation, linear wave equation. We saw the graph and solved it using four, 5 different techniques like explicit plus CDS, then implicit plus CDS, then explicit UDS, explicit implicit UDS, Lax van der scheme. Okay. Then we came across with the higher, I told you about the higher order higher order terms discretization for CDS or UDS. Then we came across with the convection diffusion in unstructured non-orthogonal meshes. And we solved this equation using both CDS and UDS. And again, you can do the implementation for higher order schemes as well. All right. Okay, if there are no doubts, you can drop off. Thank you for the session. Bye-bye.